Now, in this demonstration, I'm going to simulate the radioactive decay problem, parent to daughter state. Radioactive decay simulation. Okay, I hope this is visible. I import libraries, numpy as np, import matplotlib.py, plot as plt. Okay, so I will start with the nuclides. So I have number of nuclides. Nuclides say 100, and the lambda value, lambda equals 0.03, right? And the daughter nuclides, okay, daughter nuclides, I say this is the ND. Start, these are 0, and if NP equals number of nuclides, right? Number of nuclides. That is the state at T equals 0. And now, okay, and now all nuclides, for all nuclides, I will generate a number to represent its state. And if it is less than the probability of decay, I will say that it is going to transform into the daughter nuclide, and otherwise it will stay as parent nuclide. So here we go. So I write here for I nuclide in range nuclides, right? Ith nuclide, it seems to be a bit confused, so I write I nuclide, ith nuclide. So for all these nuclides, so I say x equals numpy random dot random, right? So I generate a random number which is a representative of its state. And I say if x is less than or equal to lambda value, right? It should decay, right? This nuclide will decay. This nuclide will decay. So with its decay, what will happen? The parent nuclide will be reduced by 1, and daughter nuclide will be increased by 1. That's nice. That is the simple decision. And then just to mark the end of the if statement, and I mark the end of for statement, right? And now let's print np and nd. Okay, print. I use the simple printing command, syntax np and print nd equals nd. So see the program lines for ith nuclide in range to nuclides. So I generated the random number, and I said if it is less than lambda value, this nuclide is likely to decay, right? It likes to decay, like head or tail decision. And now see the answer starting from 100 nuclides. Let's see the results. So 97 will remain in parent state, and 3 will go to the daughter nuclide state. This is the situation after one time interval. For the next time, start with these values and go for the next step. So now the nuclides has been changed. So in the next cell of the code, with all the values intact, I have just copied the program. It means I'm repeating that cycle, but with the number of nuclides of course, in the parent state, I say it is equal to NP. So next time interval. For next time interval, from 97 parent nuclide, the number is now reduced to 94, right? And daughter nuclides have been updated. So this is for the next time step. And now, just to make it a complete thing, for every time I have to do it, therefore, instead of defining as NP as one single variable, I should represent by a vector. I have a time vector, and I will have a vector for NP storing values and D storing values. So here I will program it like this. Okay, so instead of just defining one value, I will define a vector to store the values of parent nuclide. So I define it at the start numpy zeros, and I would say 50 time steps, and similarly ND as numpy zeros 50. Well, I will check whether this command is correct or not. Now this is not required. Here I write, say for example, y equal to numpy zeros 5, and see its answer to see whether I am writing correctly or not. Okay, that's the objective. I would like to create an array that can store 5 zero values. And here in the original program, I have created an array that can store 50 values. And the time steps, so time starts from time numpy a range. Okay, let's make it more generic. I say n steps, time steps. So for example, 50 time steps. So I say a range numpy a range n steps plus 1. So 0 to 50. And this should also be n steps plus 1. And similarly, this will be n steps plus 1. So all zero values. But for parent nuclide, what should be the first value? So the first value, NP of 0, the first value in the vector, it should be 100. So it should be nuclides, right? That's fine. Nuclides that we have initialized as 100. And now I start here a time loop. So I say for daytime range, so we have to look for 100 steps. So after first step, I say 1 to n steps, right? 1 to n steps to take the value of the available parent nuclides, and generate a random number for every nuclide. If the random number is less than the lambda value, then it's a decay. Otherwise, the nuclide will remain in parent state. So here I would say it is the nuclides equal to nuclides plus 1, right? And okay, daughter equal to daughter plus 1, right? And let's initialize before that the daughter nuclide somewhere, daughter equal 0. But it is not very nice here. Let's shift that to the beginning of the program. So start with the 100 parent nuclides, 0 daughter nuclide, probability of decay time steps, and then we have defined the vectors to store the values. And after that, after this loop, in every time step, we will store the parent nuclide and parent of daytime. It's equal to the nuclides, available nuclides, and n daughter at ds time will be equal to daughter, right? And this will end the loop for time. This will end the loop for time. And finally, instead of printing the results, let's quickly plot the results. Plot time variable is available or not. Yes, we have created a vector time. And here I will plot NP. P as blue circle and time ND as red circle. And that's it. So in every time step, for the available nuclides, we generated random numbers and saw how many will decay or not. And let's see. So program has crashed somewhere. Okay. A small syntaxal mistake. Okay. And then now I got success. And let's see the expression of my success. Have I simulated radioactive decay or not? Oh. Both are increasing. Oh, okay. Sorry. In both expressions, it is written as +1. So this is the process that computer scientists will not understand you. So you have to solve your problem by yourself. Behold, radioactive decay. Parent nuclide, the blue one is decaying and the red one is increasing. The last number, because the daughter nuclide was all set to 0, therefore the last value is shown as 0. So I can correct it. That for n parent, I can say it should be from 1 to n steps plus 1. And for n daughter, okay, 1 to steps plus 1. It has crashed. Okay, it should be from 0. Okay, that's it. But now if I change the number, say 1000, so it will be more elaborate picture. Is it really radioactive decay? How many of you believe it's radioactive decay? we have seen the number of nuclides at different time steps. Let me give you the proof. Well, there is some problem. I will look into that. But let me show you one more thing. Hot and now, sorry, time and P will be again blue dot. The radioactive decay is exponential. What's the proof? I have a proof that I say y scale log. We know that the exponential relationships fall on a straight line if we have the semi-log paper. So I'm showing the parent nuclide graph. Straight line. Monte Carlo works. And I'm still teacher.